Okay, all right. So today we will continue covering numeric optimization. So we've covered root finding methods, and then we talked about finding derivatives, and then we said we could apply any of the root finding methods to a derivative, and that will help you find a local min or local max. Today we have golden section search, which is a numeric method for finding a local minimum, and if you apply it to negative of f, then it can be used to find the local maximum. And it's based on the golden ratio. So the golden ratio is around like 1.6-ish, okay? And the idea is if you have this rectangle where one side has a length of 1 and the other side has a length of 1 plus x, this resulting rectangle, after you remove a square, this resulting rectangle has the same proportions as the original rectangle. That is, the length, the short side of this remaining rectangle to the long side. That means the ratio of x to 1 is the same as the ratio of 1 to 1 plus x. Okay, so this thing, the length from x to 1 has the same ratio, as 1 to 1 plus x. So that's kind of the idea. And then if that's the case, then the ratios continue. This ratio of 1 minus x to x has the same ratios as x to 1 as 1 to 1 plus x, and so on and so forth. And you can kind of keep going and keep cutting off squares, and you'll have a rectangle remaining, and then you'll get like this spiral. I don't know, the golden ratio spiral that actually shows up in nature for like the nautilus shell and things like that. And it's it shows up quite a bit. So anyway, the ratio between the blue length and the red length is the same as the blue length to the red length for wherever it is. So we have I guess here, I did 1 to 1 plus x is x to 1. And if you solve for x, so if you take this ratio, 1 over 1 plus x is the same as the ratio of x over 1, solving for that, you're going to get x is equal to 0.618, something around that, okay? And so 1 to basically 1.618 is the same ratio as 0.618 to 1. So this is just kind of solving for that. Okay, so you can see that if I do 1 divided by 1.618, I get around 0.618, which is kind of a neat thing. And the other thing is that when you do 0.618 squared, you get about the same value as 1 minus 0.618, okay? So there's kind of this interesting property of this golden ratio that, you take this quantity, and if you square it, you also get 1 minus that. And golden section search takes advantage of this property so that we can reuse our values in searching for a minimum. So the way it works is, let's say you have some kind of function, right? So here's just a very simple function, x squared minus 0.8x. And, visually, if we plot this, we can see that the minimum is going to be at 0.4, and we can solve this easily ourselves, okay? A lot of times, you might not, the idea of, plotting a function could actually be, very computationally expensive, right? So the way a computer plots a function is that it doesn't actually know that this is a parabola. All it knows is, we're just asking it, okay, plug in 0 and give me a number, okay? Plug in 0.01 and give me a number. Plug in 0.02 and give me a number. And then it just connects the dots, okay? So the computer doesn't actually know this. I just asked it to calculate a whole bunch of these things, and then we just connected the dots. And the dots are so close together, or the points are so close together, that it looks like a smooth line. But this actually required a whole bunch of calculations. And for a simple function like this, it happens almost instantaneously, and it's not that big of a deal. But you could have another function that takes longer to compute. Like each computation could take a while, and so in those cases, you might not have the luxury of having the function plotted. Okay, but the idea is that you have some kind of starting interval, and you know or suspect that there is a local minimum somewhere in this interval. So, in this thing we can see there is a local minimum somewhere, okay? And in this case it's also the global minimum. But anyway, the idea is you just have some function and you're going to say, hey, we're going to start with some interval, and I think there's going to be a local minimum somewhere inside this interval. You don't actually have to have the function plotted. And what you do is, so here's my interval. It's going to go from 0 to 1. And we're going to say, I think there's a local minimum somewhere inside this interval between 0 and 1. Okay? And that's it. Okay? So here, the endpoint of my interval is 0. The endpoint of the interval is 1. Okay? So I'm going from 0 to 1, and we're going to search for the local minimum somewhere in here. And what I do is I calculate the value of the function at two locations, okay? The two locations will basically be at 0.618 and 0.382. I'm going to just take the golden ratio, right? So the golden ratio going from 0 to 1 is around 0.618. I'm going to go from the golden ratio from this end to over here, which is going to take me to 0.618. And then I go the golden ratio length from 1 going towards 0, which will take me to around 0.382. Okay, so if I have my left bound, okay, I go the golden ratio over this way, and then I have my upper bound, I go the golden ratio over this way, right? So I take basically the length of the upper bound to the lower bound, UL, I multiply that by phi, which is 0.618, and I do lower bound plus this, and then I do upper bound minus this. All right, in our case, because the lower bound is 0 and the upper bound is 1, it gives us nice easy numbers of 0.618 to 0.382. In some other interval, you might not have such nice easy numbers, but you just kind of follow the same principle. You take the difference between the upper bound and lower bound, multiply that by the golden ratio of 0.618, and then you go that distance from the lower bound to the upper and the upper bound to the lower. Okay. So anyway, I'm going to evaluate at those two locations, 0.618 and 0.382, right? And so this is my my values, x1 and x2, and then I calculate the value of the function at x1 and I calculate the value of the function x2. And I see that the function at x1 is higher than the function at x2. So, it's almost like maybe it makes it a little bit too easy to see. But if we see that this value is higher than this value, then we know for a fact that the local minimum cannot be to the right of x1. Okay? All right? So because f of x1 is greater than f of x2, we know that the minimum value, okay, which in the beginning we said there is a minimum value between L, the lower bound, and the upper bound. Okay? We're going to say that the minimum, at least a local minimum, there has to be at least a local minimum between the lower bound and x1, because if we're kind of going under the assumption that there's just kind of, if there's at least one, we know there's at least one point that's lower than x1 between L and x1. So, and that's x2. Okay? So because we know this point is lower than this point x1, we're going to say if there's a side to search for a local minimum, it's going to be this side. Okay? That we're going to just ignore the side to the right. Okay? Now, I mean, there could be if you had multiple local minimums within your bound or within your interval, okay, there could be another local minimum, and perhaps even a local minimum that's even lower. Okay, but we're going to say, hey, if we're going to focus our search on one of these sides, the side to focus our search on is going to be this side, because we know there's at least a point that's lower than x1 on this side. So we're just going to throw away this side, okay? So we throw away this side. Is that okay? And so now my lower and upper bound go from 0 to 0.618. Okay, so that's my new lower and upper bound. And then, and I go and I repeat the process, okay? So I have my lower and my upper bound from 0 to 0.618, and I'm going to search for kind of 2 points near the middle, okay? And so this is where the kind of the genius of the golden section search comes in, okay? Is that if this is my new lower and upper bound, and if I want to go phi 0.618 from the way from the lower to the upper bound, where does that take me? That takes me to 0.382. Remember, 0.618 squared is 0.382. And so if I go 0.618 of the way over to here, that's going to take me right here. So this value, which used to be my x2, is going to be my new kind of value that I find from, going 0.618 of the way going from here to here. Okay, and so I don't have to actually find two new values. Okay, I only have to find one new value. I have to go 0.618 of the way from here down to here, right? So going, 0.618 of the way over here, that's going to take me over to here. Okay, so this value x1, I've already calculated its location at 0.382, and I've already calculated the value of the function at this location. I don't actually have to find a new value and run it through the function, right? So again, this is a simple function. It hardly costs our computer anything to compute it out, right? But you could imagine there's some complicated function where every time you want to evaluate a value, like maybe it takes 20 seconds to run or something, right? Like it's kind of like when you did, what was it? When you had to do RVest and you had to go to the server, like every page you went to, like it took a few seconds and you had to wait, right? And so you could imagine there being some kind of function or some kind of process in the future where every time you want to calculate a value, it takes a while to compute it, right? So you do, like if you can reuse values where you don't have to recompute it, like that's going to save your computer some time. Mm-hmm. So the genius of golden section search is that, hey, we can just reuse that old value. We already have the value for here, right? We calculated this value back in this step, so I'm just going to use it again. I don't have to recalculate it, okay? And I only have one new value to calculate, okay? So the old x2 becomes my new x1, and then I calculate my new x2 value, which is going to be 0.618 of the way from 0.618 to 0. So that's going to give me 0.236. That gives me this location. And I do the same kind of thing. We know there's a local minimum somewhere between the lower and the upper bound. And we know after evaluating the function, we know the function at x2 is higher than the function at x1. So if we're going to focus our search on one of these sides, we're going to focus on the search between x2 and the upper bound. And we're going to eliminate everything to the left of x2 because we know there has to be, if we're going to search for something, we know there's at least one value that's lower over here. So let's keep searching on this side. So we're going to throw away, we're going to throw away over here, everything over here. Okay. And again, because of the golden ratio, this value, which is over here, this is going to be 0.618 of the way from here to here. Okay. And we can kind of continue using this golden ratio where we don't have to find two new points. We just have to we just relabel the old point that we had, and then we just have one new location to keep searching for. Okay, so I come and I find. So I evaluate this over here, and I say, okay, which one is lower? All right, and the yellow one is lower, so we're going to eliminate everything to the right of blue. Okay, and we keep going. And we say, all right, which one's lower? And we're going to eliminate everything to the left of this line. And then we say, okay, which one's lower? And here it's actually hard for me to spot which one's lower. I don't actually know. Okay, apparently that side was lower, so we eliminate that side. And you can see, every time I eliminate one of the lines, like this line gets reused, okay? And then here we're gonna throw away everything to the left. This line over here gets reused, right? So you're gonna see that same dotted line, right? And then between here and here, these two, this one's higher, so we're gonna reuse this line right here, okay? And then, and I think this side's higher, so we're gonna, every time I eliminate a side, we're gonna reuse one of the other lines, okay? And the kind of our boundary, our interval for where we're finding the local minimum, gets smaller and smaller and smaller, okay? And so we just kind of keep repeating this process each time our interval shrinks a little bit, okay? And it shrinks at a linear rate, okay? So this is, kind of like bisection method where we have linear convergence. It doesn't converge super quickly or anything like that, but that's okay. It works, right? And in golden section search, kind of like bisection method is pretty robust against, getting stuck. Like Newton-Raphson method frequently gets stuck on stuff and things like that. Golden section search, kind of like bisection method, works pretty well. So it has linear convergence, so it's among the slower converging ones, but again works well. Okay, and so so this is what we have. So golden section search, it says golden section search is very robust. If a minimum lies within the interval, it will find the minimum. If the minimum lies on the boundary of the interval, it will converge to the boundary, right? Okay, and if multiple local minimum exist, it will find at least one of those things, okay? As far as termination conditions go, you often just pick some arbitrary value, some arbitrary tolerance, and you say when the difference between the upper bound and the lower bound is smaller than some quantity, we'll go ahead and stop, right? So depending, again, keeping in mind the limits of floating point numbers, you can say, okay, if we're dealing on, the scale of 0 to 10 or something, we're going to say, okay, if the difference is less than 10 to the minus 6, then we'll go ahead and stop. But if you're on the order of 10 to the 100, okay, then you might have to stop on, if the difference is, less than, I don't know, 10 to the 20 or something, right? So, different orders of magnitude for the difference that you are searching for. Okay, let's see. Let me go ahead and give you your first view quiz answer. What is it? Week 8, Monday. First view quiz answer is the letter C. C as in cat. C as in cat is your first view quiz answer. All right, so this is some code that will do golden section search. I've adapted this. So this was a different person. Eric Kai wrote this up, and I kind of adapted it. And so anyway, we calculate the value of phi, -1 plus square root of 5 over 2. That's going to give us 0.618. And the arrangement of points is lower bound x2, x1 upper. So x1 is going to be lower plus phi times the difference between upper minus lower, and x2 is going to be the upper bound minus phi times upper minus lower. We're going to evaluate the function at f at x1 and f at x2. And then we're going to say there's some tolerance. By default, I used 10 to the minus 5. We're going to say while the difference between the upper and the lower bound is greater than our tolerance, we will run the following algorithm. So we evaluated the function at x2, evaluated the function at x1. If f2 is greater than f1, okay, if this value is greater than this value here, then we know that the minimum is to the right of x2. It's going to be between x2 and the upper. So x2 becomes our new lower bound, x1 becomes our new x2, and then f1 becomes our new f2. We're going to calculate a new x1 value at lower plus, now that we've calculated a new lower bound, phi times upper minus lower. And then now that we have a new x1, we're going to calculate f at x1, and that's going to be f1. Okay? And then otherwise, we just do the opposite. Okay? If x2 ends up lower than x1, then x1 is going to be the new upper bound. x2 becomes the new x1. f2 becomes the new f1. Okay? And again, these are just reassignments. We're not recalculating anything, and we only make one call to calculating the function. Okay? Now we've calculated a new location for x2, and we calculate the value of the function f at x2. And so again, this really minimizes how many times we have to call the function. And we've been using a simple function, but imagine if your function was computationally expensive to compute, by minimizing how many times we're calling f, we're saving ourselves clock cycles here. Okay, and then so we do that. And then we'll increment our number of iterations by 1, and then this just keeps running. This is the while loop, and we just keep doing over and over and over again until the difference between the upper and lower bound shrink below our tolerance. Okay, and then at the end it just says cat converged in blank iterations, and what it will return is it's going to return the midpoint of the lower and upper bounds. Okay, so we can try this out. We can try out our function f being x squared minus 0.8 times x. And I run golden section search. And I say my tolerance is 10 to the minus 5. And it says it converged in 24 iterations. And the value, its best guess for its local minimum is 0.399999, which is pretty good. Okay, we know the true value is at 0.4. And again, all numeric methods give you an approximation, right? If we're looking for exact answers, numeric methods aren't the way to go. But we're just looking for something that's close enough, and I'd say this is close enough, right? You can say, I want an even lower tolerance, 10 to the minus 6, all right? And it says, okay, it took me 29 iterations, and this is your answer. Okay, 10 to the minus 7, it gives me 0.4, probably not exactly 0.4, 0.000000 something, okay? And it said 34 iterations, and if I decrease my tolerance to 10 to the minus 8, it is able to do it, and it does it in 39 iterations, okay? And you might see every time I decrease my tolerance by an order of 10, it took me 5 additional iterations, okay? And that's because if you remember the amount we're kind of shrinking by, the next interval is around 0.618, the size of the previous interval, right? Because we're throwing away around 0.382 every single time. When you take phi and you raise it to the 5th power, it's around 1/10, make it around 1/11 of the previous size. So phi raised to the 5th power is around a little under 0.1, and that's why it takes around an additional 5 iterations to shrink your interval by a magnitude of 10. Okay, so if you want to shrink your interval by a factor of 10, I guess to produce an additional decimal place of precision, it will require around 5 additional iterations, which for a simple function, your computer can compute 5 additional iterations, no problem. Okay, but again, you might run into some complicated function in the future that each iteration takes like a second. Okay, and then you might want to think about how often that takes. Okay, so that is golden section search. And now I want to show you coordinate descent. So everything we've seen so far has been for one-dimensional functions, unidimensional functions. And to be honest, it's really again, except in the most extreme cases of functions, it's pretty easy to find a minimum for a unidimensional function. We can do something called the grid search, which is the most rudimentary way to find a minimum. Okay, and a grid search just says it's basically what we're doing when we plot this. Okay, so when we plot the function, the plotting of the function is basically a grid search, in that we just say, hey, evaluate the function at 1,000 different points. okay? And then, and which one's the smallest? Okay, so here, when I plotted this, I asked the computer to evaluate this function at probably like 100 or 1,000 different points. I don't remember what I put in, and it evaluated, and I said, okay, connect all those points you evaluated with a line, and it connected the dots, and it plotted this graph. Okay, and then we look at this graph and we go, it looks like the local minimum's right here, and that would have sufficed. Okay, as far as searching for a minimum, that's a grid search. It's probably the least efficient way to go, but you can do a grid search. Grid search is done by evaluating the function at a whole bunch of locations. So I could say evaluate the function between -3 and +3, spaced out 0.001. Okay, so there's 6,000 locations to evaluate. And I say, okay, which of those values was the smallest? And it says the 3,401th location. And I say, okay, what value does that correspond to? And it says that value is 0.4. Okay, that's a grid search, all right? And, if it's a simple function, evaluating the function at 6,000 locations hardly takes any time, and we can do that, okay? So grid search is fine for a unidimensional function. So I know we've been covering all of these things, and I said, Newton-Raphson and this and that, and those are great ways to do it, and you can get your local minimum in about 5 iterations. Okay, with golden section search, it took us 24 iterations, 39 iterations, or something like that. But if it's a simple function, you've got the computational power, just say, hey, computer, do 6,000 operations and give me the smallest value, and my computer barely breaks a sweat. Okay, so when all else fails, just do a grid search, right? But the grid search becomes really, really, really inefficient when you have a high dimensional function. Okay, so if you have a multi-dimensional function, so even if we just go from 1 dimension to 2 dimensions, my grid search becomes way more complicated, right? Because now a grid search, I'm going to have to evaluate 6,000 locations in the horizontal direction in x1, and I got to evaluate 6,000 values in x2, and basically all of the coordinates between them. So if I say if we're going to search from -3 to the corner -3, -3 to +3, +3, and we're going to search there, now I have 36 million locations to evaluate if I'm doing a 2-dimensional grid search, right? So 1-dimensional grid search, no problem. 2-dimensional grid search, way harder, 36 million, okay? 3-dimensional grid search, okay? Now we're in the billions, okay? And then, it's not uncommon to have like a 17-dimensional function, okay? So, when you do linear regression of multivariable linear regression, you might have a whole bunch of variables going on, and if you want to evaluate something, you might have a function of 17 variables or something like that. And so to do a grid search on a 17-dimensional function, that would absolutely break your computer, okay? Doing 36 million operations, that's going to take a lot. I don't know what happened here. Doing 3-dimensional things. So anyway, when you have multivariate functions, grid search no longer becomes an option. So we have to think of strategies to deal with these multivariate situations. In 102B, you will learn something called gradient descent. Okay, so gradient descent is a very common optimization algorithm. It's a lot like Newton-Raphson method, but it's for multivariable situations. But that involves finding the gradient, and it's a few extra lectures. And so that's 102B, where we do some linear algebra and stuff. Okay. In our class, we won't do gradient descent. We're going to do something called coordinate descent. And coordinate descent basically says, okay, you've got a multivariate function. Let's reduce it to a univariate function. Okay, we can do optimization on a univariate function, And we kind of do this iterative method where we take the complicated multivariate function and we make it a univariate function, okay? So that's what this is. Coordinate descent. Coordinate descent algorithm is an optimization algorithm that searches for the minimum of a multivariate function by performing univariate minimization in one direction at a time, okay? So we achieve this by selecting one of the variables. So you got this multivariate function. We're going to select one variable to minimize. And then what we do is we say all other variables in this function, we're going to kind of lock into place. Okay, we're going to keep, if we're going to minimize x1, we keep x2 constant, x3 constant, x4 constant, all the other variables constant. And then now there's only one variable that can vary, right? And then so we reduce our function from multivariate to a univariate function, and then we minimize that, okay? So we perform minimization on that kind of our reformed function. And once we determine the minimum in this direction, then we go to the next variable and we perform univariate minimization for the next variable, okay? To illustrate this, I have a little bit of code to kind of illustrate this. So I've got this code example. I think I posted it on Canvas. Let me go ahead and give you your second view quiz answer. Second view quiz answer is the letter D. D as in dog. D as in dog. Okay, so so I have golden section search loaded up here. And so golden section search will be able to, I can call golden. If I create a function f is a function of x. And we're going to say, x squared minus 0.8 or 0.8 times x, okay? And then I can do golden, find the minimum of f between, say, 0 and 1. And, and it runs through its cycles and it says, here's your minimum at 0.39999, okay? So we're going to basically use golden section search to perform univariate minimization. And then I'm going to do coordinate descent. Now, I've posted this, and I want to say this code that I've written is intentionally not great, all right? And it's just to show that it's working one step at a time, okay? Just to emphasize that we're doing one step at a time. And because in your homework 5, I asked you to write a coordinate descent algorithm. And so you can kind of use this as a starting point, but obviously you want to find a better way to write your code, okay? But I use a library called Plotly, which allows me to create cool little 3D graphs over here. So I'm gonna load up the golden section search function. This is gonna be our function that we want to minimize, okay? X squared minus 2x minus 0.5xy plus 2.5y squared, okay? Now with this, I can actually go to, say, Wolfram Alpha, okay? And I can put in that function, and I can, this is gonna work. And it plots it, and I guess this is what the function looks like, and we can see, where is, where's the minimum? Okay, minimum of. Okay, so it finds the minimum. The minimum is located at 40 over 39 and 4 over 39, x and y, and then it says here's your contour plot, and this is where your minimum is located. Okay, so that's thank you, Wolfram Alpha, right? It's a beautiful website and stuff. Well, anyway, what we're going to do is that's the function that we're going to try to find the minimum of, okay? So here's my function g, okay? And what I'm going to do is I'm going to create I'm going to plot the function, okay? And here I do outer. What outer does is it's going to apply this function and give me a matrix of this, right? So I said sequence plot going from x from negative 1.5 to 3.0. So x goes from, I don't know, is all of these locations. And then y is all of these locations. And then if I do outer x, y, and g, okay, it's going to create as basically a 71 by 71 matrix, okay? And it calculates the value of the function at, I don't know, what is 71 squared? 71 times 71, 5,041. So I'm doing kind of like almost like a miniature grid search, but this is just so I can kind of plot it so you can kind of see. So I'm going to run plotly, okay? And this is what plotly produces based on this thing. Okay, so this is kind of the what the function looks like. It looks like this, and we are going to search for the minimum, which is somewhere around here. Okay, so I don't know. This is kind of what this paraboloid looks like. Okay, so anyway, I'm going to just start arbitrary starting location at negative 1, 1.5. Okay, so this is going to be my arbitrary starting location, this orange ball right here. Okay, so this is where we're going to start. And what we want to do is we want to, starting here, we want to kind of find the bottom. All right, so gradient descent would actually find like the multivariable like gradient, and it would point us in the direction of steepest descent, and then we would go in the opposite direction. It would basically roll the ball downhill. But we're going to do coordinate descent, and so we're going to say, okay, my starting x0 is negative 1, and my starting y0 is 1.5. And so what I'm going to do is if I look above and I say y is equal to 1.5, I am going to lock 1.5 in place, okay? And so, my function used to be x squared minus 2x minus 0.5x times y plus 2.5 times y squared. I'm going to replace y with 1.5, okay? And so now, this is just a function of x, right? I replaced all locations of y with 1.5, and so now my function is just a function of x, okay? And this is going to be the function that I want to minimize. And so in plotly, I'm going to trace out that line, okay? So so you can see here is y equal to 1.5. I've traced out that line, and so now I have a univariate function, just this parabola right here, this orange line here, and we're going to minimize this. Okay, so I've locked that into place, and so to find the minimum, I mean, I could find it in multiple ways, right? Like I could look at this and I can use calculus and say, okay, if I've got x squared minus 2x minus 0.5x times 1.5 or whatever, I can say, all right, use calculus and find the minimum, okay? But I'm going to just go ahead and use golden section search, and I'm going to say golden section search, what is the minimum of this function? And it says when y is equal to 1.5, the minimum of this function for x1 is 1.375, okay? And if you did calculus and you just said, all right, take the derivative, set this equal to 0 and solve, you would also get 1.375, okay? So I'm going to go ahead and add a marker, and basically we're going to add a marker to the bottom of this orange parabola. So, so I'm going to do that. And this this white dot right here represents the bottom of this orange parabola, right? So I've basically, I'm taking a slice of the three-dimensional structure, or this two-dimensional function, which is just this one-dimensional slice, and we're going to find the minimum of that, okay? So now that I've found the minimum here, I'm going to hold this value, 1.375 constant, okay? So if y is locked in at 1.5, I'm going to x, we found the minimum to be 1.375, and I'm going to lock that in place. And so basically, here's my previous function, x squared minus 2x and whatever. I'm going to basically replace all of my x's with 1.375. So I got 1.375 squared minus 2 times 1.375 minus 0.5 times 1.375 times y plus 2.5 y squared. All right? So now I have a function just of y. So that's going to be my function g at iteration 1b. And I'm going to go ahead and I'll plot that line. Okay? And so now I have this kind of this white line showing this is, I'm holding x constant at 1.375. And now it's kind of hard to see, but basically I have this white line. And we're going to trace, we're going to minimize this white function. Okay? And so, so using golden section search, and again, I could use calculus to find the minimum of this, but we're just going to ask golden section search, find the minimum of this thing, and it says, oh, the minimum value of y over here is going to be 0.1375. Okay. All right. Does this kind of make sense what I'm doing? So I'm going from a two-dimensional function, and then at each iteration, I'm locking in kind of the other coordinate, and I'm allowing only one of the variables to vary, and we minimize it one variable at a time. So so using that, I'm going to go ahead and put a marker at y equal to 0.1375, which is this yellow dot right here. So that's at the bottom of this this white line. Okay, and then and I kind of just repeat it again and again. So I say, all right, let's lock y into as 0.1375. I replace y with 0.1375, and then we'll go ahead and we'll plot the line there. All right, so this is and you can see we're getting closer to wherever this bottom is. Okay, and so here is y locked in at 0.1375. You know, there it is. And then we're going to say, all right, where is the minimum of this thing, right? And so we could say, okay, the minimum of this thing is going to be somewhere over here. So so we do a golden section search, find the minimum there. And so x2 at this location was 0.1034375, right? And so on this yellow line, okay, the minimum is a little bit over here, and now we're going to lock that into place, okay? And we would continue going on and on and on. I would draw another line locked in here, and we would minimize that, and we would kind of iterate repeatedly, okay? So you just kind of, you have this higher dimensional function, and so, you know, on my computer, you know, I have a two-dimensional function, and I basically lock one of the variables in place. I have that reduces it to a function of one variable, and then we minimize that, okay? And it works for higher dimensional functions as well. If you have a 5-dimensional function, you would keep 4 variables locked in place. Only one variable can vary, and so that becomes a univariate function. You minimize it in that direction. Then you go to the next variable, okay? And you say, all right, we're going to lock x1, we're going to lock x3, x4, and x5. We allow x2 to vary, and then you minimize the function in x2. And you kind of just go one variable at a time, and you minimize in that direction. And in a lot of functions, it works well. There's going to be some functions where, like, you can get stuck in some kind of weird loop or some kind of thing where it doesn't work super great. But for a lot of functions, coordinate descent works quite well, and it doesn't require calculating the gradient, which, you know, gradient descent is a great algorithm, and you'll learn that in your next class. But coordinate descent does not require calculating the gradient, and it allows us to, you know, employ univariate optimization, which is generally a very quick method, and it allows us to approach multivariate functions despite basically only having a univariate optimization algorithm under our belt. Okay, well, all we have to do is we just reduce the complicated multivariate function down to univariate functions, and then we apply our optimization methods there. Okay. Anyway, so this is a little bit of Plotly. I barely know how to use Plotly. I just know enough to draw this thing. But it's kind of a fun little thing that you can rotate stuff around, which is kind of cool. And again, the code I've written is intentionally kind of bad, where I manually replaced y with 0.1375 and things like that. And in your homework, you're gonna write up a little algorithm, write some code to implement coordinate descent, and you'll want to write better ways, or come up with better ways to produce your intermediate functions and things like that. Okay, let me go ahead and give you your final view quiz answer for today. The last answer is A as in apple. A as in apple is your last view quiz answer. Okay, we'll go ahead and end here for today. I hope your homework assignment's going well. You have a question?
So, when do we know that we can stop the iteration?
Oh yeah, when do you stop? Basically, you can evaluate. I guess when your step sizes, you can ask what's the difference between x1 and x1 at this iteration and the next iteration. What's the difference between x2 and the next iteration? You can do that. You can also ask what's the difference between the function at x1 and the function at x2, every time you minimize. So basically, there's lots of different criteria you can say, and basically when the difference shrinks below some kind of tolerance, that's when you can stop. That's that. Okay, we'll end here for today. Have a great rest of your day. I hope your homework's going well, and we will see you on Wednesday.